Hello! In this video we will discuss the concept of the moment of inertia, an important quantity for rotations, and we will see how to calculate it. Previously we have used the expression F equals ma quite a bit. We can rearrange that expression like this. This says that the acceleration of an object is the force it experiences divided by its mass. The larger that mass, the less effect a force has on an object's acceleration. For that reason we can say that mass is a property of an object that resists changes in its velocity, or motion. Because an object that does not change its velocity is said to be inertial, the mass is often called the inertial property of an object. After all, it controls to what extent an object maintains its current velocity. With rotations, we have something similar, that we call the moment of inertia. It is usually denoted with a capital I. To show how this works similarly, we are going to write an equation that is pretty important for rotations. This equation says that the torque equals the moment of inertia multiplied by the angular acceleration. Let's just rewrite that as this. Now, torque is related to the force and is kind of the rotational equivalent of force, since torque is the cause of an angular acceleration, just as a force is the cause of a linear acceleration. We'll talk more about torque in a different video. We can see, though, that I serves a very similar role in this equation as the mass does in the equation for force. The torque causes an angular acceleration, but it is reduced by the moment of inertia. The larger the moment of inertia, the less effect the torque will have. This is just like how the effect of a force is minimized if the mass is large. So when talking about rotations, the moment of inertia is going to stand in for mass. In fact, some people call it the angular mass for just that reason. A more common term is rotational inertia. So now that we have some understanding of what the moment of inertia does, let's talk about how to calculate its value. Let's start with the simplest case. We have one object that is rotating. But the thing is, an object can rotate in a lot of different ways. For instance, we can have this line here at a distance of, say, 5 meters away, and we can have the object rotate around the line, keeping a fixed distance of 5 meters. We would call such a line an axis of rotation. However, that line could also be 10 meters away from the object, in which case the rotation would look more like this. Obviously, you can imagine that we can choose any distance away. However, the direction of this axis of rotation can also change. We can have an object rotate around this axis instead. And finally, we can also have the axis point into the screen, in which case the rotation looks like this, and is in the plane of the screen. Now, the value of the moment of inertia depends greatly on where this axis of rotation is. Now, if the object has mass m and is rotating around this axis here, which is pointed into the page, and is a distance of r away from the mass, then the moment of inertia is given by this formula. As a quick example, if the mass was 5 kilograms and the distance was 2 meters, then the moment of inertia would be 5 times 2 squared, which is 20, and the units would be kilogram times meter squared. Now, if the axis instead passed through this point here, 4 meters away, then the moment of inertia would be 5 times 4 squared, which is a value of 80 kilogram times meter squared. So the placement of the axis matters a lot. The further away it is, the more rotational inertia an object will have. Now, what if the axis of rotation was this line here? What value do we use for the distance between the object and the axis? After all, this line here is obviously longer than this line here. The answer is we find the shortest distance between the two, which is the path that is perpendicular to the axis. All other lines will be longer. Now, this is great for one single mass, but what if we have a few different masses that are attached together, in such a way that they don't move relative to each other? For instance, imagine a dumbbell, where the weights are so heavy that we can ignore the bar that connects the two of them. Then we can just treat it like there are two masses that are rigidly attached to each other. Now let's say we rotate this dumbbell around this axis here. What will be its moment of inertia? Well, the rule is that we find the rotational inertia of each mass, and we add them together. So this mass will have a moment of inertia of mass times r squared, and so will this one. So then we add them together, and the rotational inertia for the dumbbell as a whole is 2 times mr squared. Of course, it doesn't have to be true that they both have the same mass and distance to the axis. They could be different. In that case, we would have gotten this result. In general, we can write this equation. It might look a bit scary, but all it's saying is that the moment of inertia is the sum of each mass times its distance squared. Now, what if the axis of rotation was like this? Well, in this case, we would actually get the same result. since the perpendicular distance is the same. Now, what if this were the axis of rotation? Well, again, let's consider each mass. The one to the left has a mass of m, and its distance is, well, its distance is 0. So its rotational inertia is 0. The same is true for the mass to the right. So the total rotational inertia is 0. That's interesting. When you plug it into this formula to get the angular acceleration, you'll be dividing by 0, and that's not allowed. Before we resolve this question, I have to mention that when we have been talking about masses, we have been talking about what is called a point mass, which means a mass that is contained in an area or volume that is so small it may as well be considered an infinitely tiny point. Now, if you stop and think about it, if a point mass is on the axis of rotation, what would it mean for it to rotate? A point mass can rotate around the axis, but if it is on the axis, then it doesn't actually move at all. That is why it is fine that its rotational inertia is 0. It just means that rotations simply don't apply to it. Now, no real object is actually a point mass. The balls on the dumbbell, for instance, have their mass spread out over the volume of a sphere. In fact, the rotational inertia of a sphere when an axis goes right through its center is given by this formula, where m is the mass of the sphere and r is the radius. But if the radius is really small compared to the scale of the problem we are dealing with, then we can effectively treat the sphere as a point mass. In fact, you can find a list of the rotational inertia of all sorts of common shapes with different axes of rotation. The values of these objects are calculated with calculus, so we'll just take them as a given. But the main notion is to split these objects up into tiny component pieces, calculate the rotational inertia of each tiny piece, and add them all together. Now, that was a lot of information, so let's summarize. Rotational inertia, or moment of inertia, is a quantity that determines how difficult it is to change the angular velocity of a rotation. The larger the moment of inertia, the more it resists change. The value of the rotational inertia of an object is dependent on the distance of that object to the axis of rotation, according to this equation. The distance is determined by the length of a perpendicular line drawn from the object to the axis, which happens to be the shortest possible line. If we have multiple objects that are attached and rotate together, we add their individual rotational inertia together, and get the rotational inertia of all the objects together. Finally, we learned that if an object is not a point mass, but rather has its mass spread over some substantial volume, then it has a rotational inertia, even when an axis passes right through it. Those values can be solved by calculus, but can also be looked up in a table for most simple shapes. And that's it for this video.